Good morning, everyone. Today we're going to try to cover two lectures. So lecture number 9 is early age properties, and the next lecture is mixed design of concrete. So we try to design our own concrete. Okay. So early age properties, including workability and also reality of concrete. Okay. So by definition, workability is the amount of mechanical work or energy required to produce a fully compacted concrete without segregation and bleeding. Rheology is defined as the science dealing with the deformation and flow of the materials under stress. Normally, we use a shear rate and shear stress curve to describe a rheology of concrete. Okay. In this class, we focus on workability and not on rheology. You should know what is workability and rheology. Consistency, we discussed this before, is defined as how easy the concrete can flow. Okay, and the setting time, we know we have initial set time and the final set time. We're also going to discuss how to measure the air content of concrete. There are many factors affecting workability of concrete. The most important one is how much water is in the system, or we say water to cement ratio. Okay. Other properties such as the amount of cement, mineral admixtures, chemical admixtures, especially water reducing agent such as superplasticizer and algae, all has an effect on concrete workability. Okay, for aggregate, the size, the shape, the volume, gradation, and even packing density can also affect concrete workability. Time, okay, so how long after we mix the concrete to check slump is obviously also important because the hydration is time dependent. Okay, temperature. Higher temperature, we have faster hydration speed. So the workability at a certain time will be lower if the temperature is higher. Okay, so we talked about segregation and bleeding before. Again, segregation is settlement of coarse aggregate to the bottom of concrete due to different reasons. For example, if the density of aggregate is very high, okay, or if the mix is too wet or too dry, okay, if the size of coarse aggregate is too big, okay, or we do not have enough fines, then we could have segregation problems. Okay. Segregation could cause lower strengths, especially on top of the concrete, and other problems. Bleeding is the separation of mixing water with cement. Okay, for example, we see some water on top of the concrete. Some of the water also trapped beneath the aggregate and also beneath the reinforcement. So that will reduce the bonding between reinforcement and the aggregate with the cement paste. How to avoid bleeding? Okay, we can increase the amount of air, entrained air, okay, or we reduce the water to cement ratio. Okay, we can also increase hydration rate if possible, or use pozzolanic materials such as slag and flash. They may also reduce bleeding. Okay. If we can also add some fibers. Fibers may also make the concrete less segregation and less bleeding. All right. So the most commonly used test for consistency, sometimes for workability, is the slump test. I think many of us has seen or even done this test before. Okay. This test has been, I believe, more than 100 years old. Okay. The test itself is very simple. We have the slump cone with the shape like this, and we fill the cone with concrete using 3 layers. The first layer, okay, and then we consolidate the concrete with steel rod for 25 times. The second layer, 25 times of stroke, and then the third layer, another 25 strokes. And then we lift the cone, we measure how much slump in inch the concrete slumped. Okay, the higher the slump value, we see the concrete has higher consistency. Okay. Again, this test is a measurement of consistency or how easy the concrete flow. Okay, but somehow we can also measure the workability or the amount of energy we need to compact the concrete. Consistency is similar to workability, but these two are different. Okay. If the concrete is too wet or too dry, we cannot use slump test. For example, for self-consolidating concrete, it is very flowable, so we do not use slump test for it. Okay. Or if the concrete is too dry, we're going to use some other test. Here shows some example of slump test. Okay. So water to cement ratio of 0.5, the slump is 10 inch. Okay, so we measure the height before and after we leave the cone. Okay, so 10 inches from here to the top of the concrete after slumped. Okay. Here shows another slump test. Okay, 8 inch. Okay, this is 5.5 inch. Again, we measure how many inch the concrete slumped. Okay, this is SEC. Okay, so SEC again is very flowable. We cannot measure the height the concrete slump because every time the height will be the same. So instead, measure the height, we measure the diameter of the concrete after it stopped flowing. Okay, we're gonna talk about SEC in more details in future lectures. If the concrete is very dry, when we leave the cone, it cannot slump. Okay, we have 0 slump. We use another test, which is called VB test, to measure the consistency of the dry mix. Okay. The test is similar to the slump test, but we also have another container. We put the slumped corn and concrete here inside the container. The container and the concrete is on top of a vibration table with a certain size. Okay. So we put a 9-inch diameter glass plate and we vibrate the table. Okay. So we transfer the energy into the concrete and we count how many seconds for the glass plate to push the concrete into that container. Okay. Again, this is for very dry mix. The VB test is not used very common as in the slump test. Okay. Sometimes we also need to measure the air content in concrete. Okay, so air content is important because it will affect the strength of concrete, the workability, and also the resistance of concrete to freeze or damage. Okay. We could use the volumetric method to measure how much air inside the concrete. The concept of this method is very simple. Okay. First of all, we put the concrete in the bottom of this container. The top portion is filled with water. And after agitation, we measure how much water in the top portion goes down. That is the volume of water go to the pores of the concrete. Okay, so we can measure the volume of water displaced. Another measure for the air content is based on pressure. We call that pressure method. Okay. So pressure method the instrument looks like this. We have aluminum container. Okay, we fill the container with concrete, again, using 3 layers. And for each layers, we roughly use a steel stick 25 times. Okay, and then we cover the container with a lid. Okay, and then we add water to fill the gap between the lid and the concrete surface. Okay, so inside this container, we have concrete, and we have cement, aggregate, water, and any type of admixtures. Okay. The only gas in that container is the air bubbles inside the concrete. So we apply a pressure, okay, into that container, and we measure the volume change. Okay. Because at this level of pressure, only the air will be compressed. The liquid and the solid will not be compressed as much. So by measure how much volume change, we can estimate the air content inside the concrete. Okay. However, this method is not valid for lightweight aggregate because inside the lightweight aggregate, we have a lot of air. Okay. When we compress the concrete, the air inside of lightweight aggregate can also be compressed. Okay. But we do not care about the air in the aggregate, only the air in the cement paste. So this method, the pressure method, is not valid for lightweight aggregate. For setting time test, before we talk about VCAT test, which is for mortar test. For concrete, we have similar instrument we call penetration apparatus. Okay. This instrument can measure how much force we apply on the surface of the concrete. Okay. Okay. So we cast a concrete specimen, and over time we measure the pressure can penetrate the concrete surface. Okay. And based on many tests, we can plot a curve. The initial set time is the time when the penetration apparatus, the pressure is 500 psi. Okay. And the final set time is the time when we have a 4,000 psi. Okay. All right. So this is the setting time test. Okay, so that's the end for lecture number 9, which is the privilege properties. Okay, very simple and short. Then let's talk about how we can design a concrete mix. Okay, so this is a very important lecture, designing a normal concrete. Okay, there's many factors affecting the proportion of concrete mix, including what is requirement for slab or workability? Okay. What is requirement for durability? Okay. The strength requirement, appearance. Okay. What is the surface finish? What is the color of concrete? If there's a requirement for that, or even the cost. The cost of the concrete. Decide how much cement and what is water to cement ratio of the concrete. Okay. So inside the concrete, we have water, we have cement. Sometimes we also have flash, slag, or other supplementary cementitious materials. Okay. You need to decide how much sand, coarse aggregate, even fibers to put in the system. And a concrete mix is defined as these properties. For example, what is the strength requirement for the concrete? This is typically provided by a structural engineer. Okay. For concrete designer, we need to decide what is the water to cement ratio. The type of algae is also pre-decided. And for us, we need to decide what is the volume for sand and coarse algae. We also need to decide the air content, the slant, the water content, okay, what type of cement we use, and how much is it, or any type of chemical and mineral matrix. Okay. So as we can see, we have many things to decide. Some of them, such as strength, is given. Some of them we need to decide using the mixed design method. The good thing is ACI, which is American Concrete Institute, give us different type of tables to select, for example, what is the water cement ratio based on exposure condition. So these are the tables provided by ACI, and we can find from the textbook. Okay. So, for example, this table is based on exposure condition of the concrete. For example, if there's a freeze-thaw exposure or if there's a de-icing solution, we can select the maximum water to cement ratio. So the harsher the environment, we should select the lower water cement ratio, or the minimum requirement for the strength of concrete. And this is another table. Okay, this is requirement for concrete exposed to sulfate. Okay, and in this table shows us the sulfate exposure condition. Okay, all based on the concentration of sulfate ions in the soil. Okay, or in as percentage or in ppm. And then we can select the type of cement. Okay, so there's at least 3 standards specify the type of cement. Okay, we are very familiar with ASTM C150, which is the standard specification for Portland cement. The 5 type of cement we discussed earlier in this class, 1, 2, 3, 4, 5 times. We have other 2 type of standard, C595, which is standard specification for blended cement. Okay, which we can see from this table. Okay, we have type Portland modified or type PM. Okay, this is similar to type 2 cement. We also have, for example, slag modified cement or SM, okay, which is similar to, again, type 2 cement. The third type of standard is C1157. This is performance specs for hydraulic cement. Okay, you can see from this table, general use, similar to type 1 cement, high strength or HE, similar to type 3 cement. Okay, this standard is performance based. Okay, so based on this table, we can select the type of cement based on the exposure condition, the amount of sulfate in the system. Okay, we can choose what is the maximum water to cement ratio or the requirement for the strength of concrete. And the next table is recommendation for slab. So based on the type of construction, for example, reinforced foundation walls and footings, we can choose the slab value. So this is maximum value 75 millimeter or 3 inch. So typically we choose the maximum value depending on the type of construction. Okay. And this is the first step when we design the concrete, to select the slab value for the concrete. And this table is the water and air requirement depending on the slump and also the size of aggregate. Okay, so based on the previous table, we select a slump. Okay, the maximum size of aggregate typically is a given. Okay, so based on the size of coarse aggregate, we select amount of water. Okay, this is in kilogram per cubic meter of concrete, and this is in pound per cubic yard. Okay, so there's two categories: non-air entrained concrete, which is the first three rows, or air entrained concrete, which is the next three rows. In the question, if it's not specified the concrete is air entrained, we assume this is non-air entrained concrete. Okay, for example, if the slump is 3 inch, and if the size of coarse aggregate is 3/4 inch, so the water content will be 340 pounds per cubic yard of concrete. The next table is to determine the air content as a percentage. This is based on the exposure condition. If the concrete is air entrained or non-air entrained concrete, and also the maximum size of coarse aggregate. Okay. So for example, for 2 inch coarse aggregate, for non-air entrained concrete, the air content should be 0.5% by volume. And the next table is to determine the water to cement ratio based on the required strength level. Okay, so this is the strength of concrete in megapascal or PSI. Okay. Depending on if the concrete is non-air entrained or air entrained, we can decide the water to cement ratio. Okay. If the value of the strength is somewhere between, for example, 5,000 and 4,000, we should use linear interpolation to determine the water to cement ratio. Okay, so using this table, we decide what is the water to cement ratio. And in the previous table, we decide how much water is needed. And based on this, we can decide how much cement is needed. Okay. The next table is to determine the bulk volume of coarse aggregate. What is the bulk volume? The bulk volume of coarse aggregate, including the total volume occupied by the coarse aggregate, including the solid particle and also the interparticle space. This is the bulk volume. In the second lab, this week, we're gonna decide the bulk volume of coarse aggregate. Another name for this is dry rounded weight of coarse aggregate. It's the same thing. So based on this table, if the size of the coarse aggregate is 1 inch, if the fineness modulus of the sand is 2.4, the bulk volume of the coarse aggregate is 0.71 cubic foot per cubic yard of concrete. 0.71 cubic yard coarse aggregate per cubic yard of concrete. Okay. If the fineness modulus of the sand is somewhere between this value, again, we use linear interpolation. Okay. So another thing we should mention is the bulk volume is dry rounded weight, which means the moisture condition of coarse aggregate is open dry condition. Okay, and to determine how much, for example, air dry coarse aggregate we need to do another calculation. Okay, which will be shown in an example in a moment. All right, so next we're gonna show you an example how to design a concrete But before we do that, we should discuss the little difference between the ACI method and the PCA method. Okay, ACI is American Concrete Institute, and the PCA is Portland Cement Association. Okay, they have two different methods, but these two methods are based on the tables provided by ACI. Okay, so that's the reason in this class we use the ACI method, and ACI method is the most commonly used method in America. Okay. All right, here is the question: to design a concrete mix based on this condition. Okay, the concrete we use for reinforced concrete footing. And the maximum size of course aggregate is 1.5 inch. Okay. The requirement for the strength, 2080 strength, 3500 psi. Here also tell us the standard deviation of the concrete strength test is 300 psi. We'll see why we need this information. For material properties, cement, specific gravity. For sand, specific gravity is 2.6, which is in saturated surface dry condition. 2.7 for coarse aggregate. The density of materials we can easily translate from specific gravity. For example, 2.6 specific gravity for sand times the density of water, which is 62.4, we get 162. Okay. The finest modulus of sand, 2.8. The dry rolled weight or the bulk density of coarse aggregate is 100 pounds per cubic foot. Okay. The moisture content, okay, we discussed what is moisture content and how we can calculate that. Okay. Of sand is 2.5% positive. Okay. For the coarse aggregate is 0.5% positive, which means the sand and the coarse aggregate are wet condition. Sometimes the moisture content is negative. So that means the aggregate will be in air dry condition. And also tell us absorption capacity of the aggregate. Okay. The first step is determine the slump value. Okay. So which is very easy based on this table. Because this is a reinforced concrete footing, we choose the maximum slump, which is 3 inch. Okay, so 3 inch. The second step, we select the coarse aggregate, which is given by the question. So 1.5 inch for the maximum size of coarse. The next step is to determine how much water is needed for the concrete, which is based on the maximum size, 1.5 inch for coarse, and also the slump. Slump is 3 inch. Okay. The question didn't tell us it is air-entrained concrete or non-air entrained concrete. So we just assume it is non-air entrained concrete. So the water content will be 300 pounds per cubic yard of concrete. Okay, 300 pounds. Okay. Then the next step, 4, is to determine the air content. The air content is depends on the size of the coarse, 1.5 inch. Again, this is non-air entrained concrete, so the air content will be 1% by volume. Okay. This is air content. The next step, determine the water to cement ratio. Okay. The question tells us the specific strength of concrete is 3,500 psi. Standard deviation is 300 psi. Okay, we should use the equation to calculate what is the required strength. The required average strength should be R prime C, the specified strength, plus 1.34 times the standard deviation. Okay, the reason for that is based on statistics. Okay, if you take CE305, I think everybody has taken that class before, and we know, okay, if the required strength is in the middle by assuming a normal distribution. Okay, so F prime C plus 1.34 times standard deviation will ensure for 90% of the time, the average strength will be higher than the required strength. That's the specific strength. Okay, so this is based on a normal distribution. Okay, that's another requirement for standard deviation. If the standard deviation is higher than 10% of I prime C, we should choose the higher value of these two equations. Higher value of these two equations. In our example, because 300 is less than 10% of I prime C, so we just use the first equation. Okay, so the required strength is 3902 psi. Okay, and based on that table, okay, so which is between 3,000 to 4,000. And because the concrete is non-iron trained concrete, based on linear interpolation, we can determine the water to cement ratio is 0.58. So in the previous step, we determined we need 300 pounds of water. And based on that and the water to cement ratio, we can calculate how much cement we need, 517 pounds. Okay, so this is amount of cement. The next step, we determine how much coarse aggregate is needed. So the question tells us the finest modulus of the sand is 2.8. Okay. The size of the coarse is 1.5 inch. So we need 0.71 bulk volume of coarse aggregate. So because 1 cubic yard is equal to 27 cubic foot. So 27 times 0.71, so we need 19.17 cubic foot of coarse aggregate. Remember, this is the bulk volume. Okay. So the question tells us the dry rolling weight of coarse aggregate is 100 pounds per cubic foot of concrete. Okay. So 17.17 times 100 is equal to 1917 pounds of oven dry coarse aggregate. Okay, so we need this much of oven dry coarse. But because the coarse aggregate in stockpile condition is not oven dry condition. Okay, and in all the mixed design, we need to determine the amount of coarse in saturated surface dry condition. So we need to do another calculation, which is the oven dry weight, 1917 times 1 plus AC. AC is absorption capacity. Okay. The reason for that is because, let me write down. Okay. Okay. You can see my iPad. Okay. All right. So we get 1917, okay, which is the oven dry weight of coarse air weight. So times 1.01, this is 1 plus absorption capacity. Okay, why we use this equation? Okay, because we need to transfer the oven dry weight into saturated surface dry weight. Okay, and 1 plus AC is equal to, AC is defined by WSST minus WOD over WOD. Okay, so 1 plus AC is equal to this, which can be simplified as WOD. Okay, so it's WOD plus WSSD minus WOD. Okay, so it's equal to WSSD over WOD. Okay, so WOD times 1 plus AC, which is this, so we'll translate into WSSD. Okay, so we need to use this equation to calculate the saturated surface dry weight. Okay, that's why we use this equation. Okay, so in the end, we need 1936 pounds of saturated surface dry coarse air weight. All right. Next step. All right. So far, we have got 300 pounds of water, 517 pounds of cement, 1936 pounds of SSD cores. Okay, and based on the density of these materials, we can calculate the volume of these materials. Okay, and also air is 1%, so 27 cubic foot times 1%. So we need this volume of air. Okay, so the total volume of water plus cement plus gravel plus air is this much. And based on that, we can calculate the volume of the sand. Okay, 27 total minus this, we need 7.76 cubic feet of sand. And that times the density of sand, 162, we need 1257 pounds of saturated surface dry sand. All right, almost there. So last step is to adjust the moisture content. Okay, so based on the mix design, we need this much of cement, 1257 SSD sand, 1936 pounds of SSD gravel, and 300 pounds of water. Okay, the moisture content for sand and gravel is 2.5% and 0.5% for sand and gravel. Okay, how we can do the moisture correction? Because the moisture content is positive, which means the sand and gravel are both wet. Okay, so which means for the stockpile aggregate, they are in wet condition. But we need 1257 of saturated surface dry sand. How much wet sand we need to get 1257 of SSD sand? We need to do 1257 times 0.225, so 2.5%, which is 31 pounds of water. We need 1257 plus 31, which is equal to 1288 pounds of wet sand. Which means we need this much of wet sand, which can think of including 31 pounds of actual water plus 1257 pounds of SSD sand. Okay, so that means the sand will provide 31 pounds of actual water. In reality, we need 300 pounds of real water. So we need to minus this 31 pounds of water provided by the sun from here, how much water we needed. And same thing for gravel. The gravel is also wet, and it will provide 10 pounds of actual water. So that 10 pounds should be minus from added water. Okay, and for gravel, we need 1936 plus this 10 pounds of surface water on gravel. So we need 1946 pounds of wet gravel. Okay, so after the adjustment, we need this much of stockpile aggregate and also water. So the water is 300 pounds minus 31 minus 10, 259. To check if our calculation is correct or not, we should add everything together and compare if they are equal. If they are not equal, something wrong over the process. Okay, so this is how much stockpile materials we need to make our first trial. So we make a trial batch, and we measure the slump, we measure the air content, and then we should adjust the mix proportion if necessary. Okay, so this is the 10th step to design a concrete mix. I will give you a handout based on the ACI method. Please read the handout. Okay. I will also give a practice question on how to design a concrete mix. I will also show you the correct answer. So make sure you read the handout and also the practice question. Okay. For next Monday, we will have our first quiz because we have discussed 10 lectures so far. It's almost 50% of all the formal lectures. So let's have an open book quiz on Monday next week. Okay. The following week, we will do an in-class mix design, which is right now we decide on October 12th. You will work as a group, which is based on the group for your lab sessions. Okay, so you will work together with your group member and design your own concrete. Okay, all right, and